everybody for joining. Like I said, this is the Getting Max Out of Max with Jen presentation workshop. And as I'd like to point out here, it is also Getting the Max Out of Max with Jen. And you'll see why I will go with this title as we go along, because it's not just getting max patchers outside of max, it is getting the most out of max using Jen. So like I said, to make sure you're ready, you'll want to have Max 8 installed and authorized, and you'll want the full Max license, not a trial or Max for Live. It would be helpful to have Xcode or Visual Studio installed because that'll ensure you have a C++ compiler for when we get along later and we have our exported C++ code and we're building our actual VST. And you'll also need CMake. It's best if you have version at least 3.19 installed to set up the projects. We won't be using most of this right away, so if you need to install those now while I'm giving an intro, you can feel free to do that during this beginning portion. Also, feel free to send messages in the chat if I'm going too fast or you need to clarify questions. I'll be happy to stop and answer any questions as we go along. So the goals for this workshop, let's see. First, I'm going to start out with a motivation for using Jen. This presentation is targeted at people that have experience, some level of experience with procedural programming languages, mostly C++. And kind of answering the question, why would I care about using Jen if I already know how to program languages, program C++ and use Juice? Why would I care about doing something in visual language like Jen when there's plenty of other, when the standard for running VSTs is, some might argue, Juice. Also, just getting comfortable with Jen patching. This workshop doesn't require you to have any experience at all with Max. It's helpful, but it's not required for this. And as we go along, you'll learn the things you need. And the bulk of the workshop is going to be practicing translating block diagrams from textbooks and white papers into Jen patchers. And that's what I'll argue later on, where Jen really shines is taking block diagrams and immediately prototyping things with them. Then another piece will be the actually getting max out of max portion, which is exploring how you can use the C++ export and basically put max anywhere. And then in this workshop, we're going to be working with Juice because that's something people are likely very familiar with. But I can also share a link to this later. I have examples of using Jen in other places. I have a Jen to VCV rack generator, and I've also tried, there are plenty of projects out there where people export to Eurorack modules and you can export to Super Collider. And the idea will be you can see what the API looks like so that if you have something that uses a C++ basis, you'll know how to take a Jen patch and immediately start prototyping for that platform. So we'll look at that. And then finally, as I mentioned, we'll actually do the embedding and exporting the code into a Juice audio effect plugin. The goal will be at the end of this, you can take home a Freeverb Jen implementation that has been exported into a Juice VST. So first, I'd like to start a poll just to see what experience people have with Max. Let's see. So this should be visible now. It's a single choice. So if you have experience with Max and Pure Data and Reactor and so on, I check off Max, but otherwise, you can fill out the other ones. Go. Cool. So most people have responded. It seems like a good number of folks have experience with Max already, which is pretty awesome. We can pass through a bunch of the setup stuff, but of course, for the folks that don't have that haven't touched it before, we'll get that sorted too. But awesome. So some people are already ready with Max experience. Cool. So Before we get into patching, like I mentioned, I'll be motivating why you should care about Gen and what it's really kind of good for. Some of this might be stuff you already know, but I'm sure some people might know that Gen is this kind of cool thing that's maybe a little scary about Max and you haven't touched it yet and you want to know more about what it actually is and how to use it. So Gen is basically, it's a self-compiling MSP object. It is a object within the Max environment that you can basically program as its own Max patch. So you can create in a very similar to Max patching way, you can create a processor that can do feedback. It can do, instead of worrying about things on the block level or the vector size level of Max, you can do things at a single sample rate. And as I mentioned, it does code generation. So in order for it to work, it has to self-compile, and you can also export that code so you can go and use it other places, which is what we'll be looking at later. And a great place to look for an overview of why you might want to care about Gen is linked here in the Max documentation. You can see that, let me zoom this in a little bit, but this will motivate a little bit of why you would use Gen. And the biggest thing to me is that if you want to design a new algorithm and hear them immediately, that's where Gen really shines, in my opinion, is you don't have to wait for something to, you don't have to go out and get your terminal and recompile something and relaunch your, or reload your VST plugins or reload whatever host environment it is. While you're in Max, everything is recompiles the Gen patcher and you can hear immediately what you're changing in your algorithm, which is just a big help, I think, for designing new audio effects. And then another thing about Gen is that there's, you don't have to worry about whether you're compiling separately for Windows and Mac. So if you have a Gen patcher and you want to share it with somebody, you can immediately just say, oh, if you have Macs here, here's my Gen code. You can try it out and iterate on designs with somebody else very easily this way. Cool. So besides what is Gen, where is it useful? As I've already mentioned, you can do as in Max, then you get flexible feedback loops as opposed to having to use specialized objects that are kind of fiddly. You get single sample processing, which you don't get elsewhere in Max. And then you can export and share with C++ programmers. If you only are a Max programmer, you can interface with your C++ friends. But as most of you are C++ programmers, Gen's also useful because of the real-time prototyping I mentioned already. It's easier to translate block diagrams to another visual language as opposed to having to turn it into a procedural program. Put an asterisk there because it does require some practice, and that's what we're going to be going through here. And there are also situations where it can get kind of fiddly because there's tons of patch cords going everywhere and it's hard to read things. And we'll also be going over some ways to make that a bit less of a problem in this workshop. How can you simplify things and abstract things so that you can be most efficient in your prototyping? And another thing is that there's a code box. There's a procedural Gen expert language within Gen. You can write procedural looking code. It's very similar to looking to Lua, if you're familiar with Lua. In this presentation, we will not be using Codebox because I'd like to make the argument that even though it's maybe familiar to folks who are used to procedural languages, that where Gen really shines is, in fact, using operators and the visual paradigm. Hopefully that'll make more sense as we go through. So to start out, even though most people have experience with Max, it'll be useful to kind of get comfortable and figure out how to get everybody set up on the same level of having their host Max patcher. So if you go and clone the repository here, this will be where most of the materials we'll be working through are going to live. And the best place to have this is somewhere on your Max path. So the best thing to do is to install it to your Max packages directory. So in my case, that is here. I have cloned this repository to my documents Max 8 packages folder. So let's see. I feel like I should give some people some time to do that while we go through. But okay, so while everybody's doing that, I will load up the first patcher that we'll be talking about here. So once you've got that cloned, I can share what this repository is, kind of what's in here. So we'll be going through all these different patchers here, 0 through 5. And in here are the starting template patchers. They're basically going to be hosts for our gen patches. And as we work through each of these examples, we'll get to a final finished solution, a different effect. And then you can also look at the solutions at the end to see if you've got the same thing. These will be the final patches. You can look inside this directory for those. Besides that, there'll also be some source. This will be where our source code is eventually, some abstractions here, but we'll get to that when we get further along in the workshop, just so you know what to look forward to. Cool. So the first thing to do is make sure you have this first patch opened up. And to get an idea of what's going on in here, I have set up the basic objects that we'll care about in the Max world that can get us started enough to work with Gen. So in here, you'll notice that there is an unlock and lock button. And this is important if you're unfamiliar with Max. When you're in a locked mode, you can't move any of these objects. They're all in place, but you can interact with the UI objects here. So for example, you can move a number box. You can scroll up and down on it. You can type into it. You can click on different messages. And here, the important object here is this Easy DAC, which turns on your audio processing. And this invites people a lot when they're new to Max, or even if you've been using it for many years and you forget to turn on the DAC and you're wondering why nothing's happening. You gotta make sure this is on. So once you turn on this, you can also notice that it turns orange or blue down here. Orange means only this window is processing audio, and blue means any patcher you have open is processing audio. I like to keep it local because then I don't have tons of things going on if I know I'm only working with one patch. Another thing is, once you unlock the patcher, then you can start moving things around. I'll turn on, I have a keycaster, so you can see when I'm using keyboard shortcuts. So if there's some keyboard shortcuts that I'm using, maybe some people haven't used before, they can get really handy when you start copying, pasting a lot of things and duplicating and trying to reconnect stuff. So hopefully you should be able to, we'll be able to share that. Yeah, cool. So that's down at the bottom here. Cool. So unlocking and locking a patcher is important. A quicker way to do that is you can command or control click on the window, and you can switch between being in a locked and an unlocked patcher. And most of the time I end up working in unlocked mode, because if you hold down Control or Command and you start trying to interact with UI objects, that also will work. It'll be as if you're in the locked mode. So most of the time you'll see me in edit mode, but if you get stuck and you can't move things, that's because you're probably locked. Cool. So another thing that we'll go through here is that we're going to be starting out with a game plug, or sorry, using Gen to make a simple game object. And we're going to be trying to replace this game here, which is allowing the sawtooth wave to go through and head to our DAC. So this is an object in native Max, but what if you want to try to do it in Gen instead? This will be our first introduction to seeing some basics of Gen. So the first thing that you'll want to do is make sure you're unlocked. and create and get to this gen patcher here. And so to actually get inside the gen window, you'll want to double click it, either in a lock patcher or from an unlock patcher, holding down Command or Control and double clicking. Cool. So most of our focus is going to be inside of this gen window and not focusing so much on the max window. And luckily that'll be nice for the people who have no prior experience, because the subset of objects that are within gen are much smaller and you can get a grasp of them easier. And something you'll notice along the way here is that actually there's a ton of things you can do with just a few separate objects in gen. So once you get familiar with those, it's more about how you connect them than the actual objects you know about in gen. And that's kind of the beauty of it. And to me, is that you can do a lot with just sums and delays and things like that. Cool. So I've unlocked my patcher here, gen patcher. And so what's going to happen when we want to have a gain? Well, all you do is you're scaling the input and you're getting an output that is scaled by some parameter. So if you say that you want your gain to be -6 decibels, oh, sorry, if double click is just selecting text, what are you double clicking on? If it's unlocked and you double click on something like same with gen. Yes, so then you're just editing you're editing the object box itself. You need to, if you're in the, if you're unlocked, you want to have Control or Command pressed when you click. Yeah. Cool. So like I mentioned, we're going to need to have a parameter which tells us what our gain is going to be. And we're going to need to scale an input and get an output. So how do we do that? The first thing that we'll need is to set the parameter. And so for that, we're going to need to create an operator within gen. And within gen, I'm going to be calling things operators. And those are these different boxes. If you're familiar with Max, you're probably used to calling them objects, but within gen, we call them operators. Cool. So to create a new object, the easiest way is to be in an unlocked patcher and hit the key N. And you'll get a new box wherever your mouse was most recently placed. And so inside you'll have this blinking cursor, and you can type in the name of what you want. So in this case, I want a parameter, and the name of that operator is param. And as you start typing in, you'll get a bunch of autofill options here. And it'll tell you in this dropdown a little bit of a help text about what those things are. So in this case, you can see that a param is an externally modifiable name parameter. And so if I hit enter on this, we're going to see that you'll notice that something pops up over here with a red dot. And it's telling you that param has no name. It's missing a name. And this is because when you have a parameter, you need to create, you need to name your parameter. So in this case, I'm going to call it gain. Cool. And so some other things that you're going to need in here besides an inlet for your input signal, you're going to need an outlet. So we've already got an inlet, we've already got an outlet, we've got our parameter, but now we're going to need to scale the input by some value. So we're going to get rid of this plus operator, because when you're scaling, you don't want to add the signals, you want to multiply them together. Or rather, you want to multiply the signal by your parameter. So you highlight, I'll undo that and show you again. You click on the object, and then you just hit backspace or delete on that object, and it'll disconnect and go away. And to use a multiply operator, you'll hit N again, create a new object, and type in star, which will multiply your inputs. If you're familiar with Max, you might be wondering why you don't see any tildes, because in Max, usually you expect something ending with a tilde to be a signal, but because inside of gen tilde, everything already is a signal, you're only operating per sample. Sure, yeah, let me zoom in. Let's go to 200, why not? Thanks for reminding me. Cool. Let's see. Yeah. So yeah, you'll notice that there are no tildes at the end of any of these things because we're all operating on one, everything happening in the gem patch is in the signal domain already. Cool. So we've got our input, and we're going to want to multiply it by this gain parameter. And at the end, we're just going to want to pass this signal out. Cool. So the way you connect things, if I should mention that, is you can either click and drag to from connection to connection, or you can just click on one outlet and then click on wherever you want to send it. That took me an embarrassingly long amount of time to know that you could do that. It's very useful if you have things going from very long distances. So cool. So now we've got our gain set up. Let's see if we can try connecting in the max window. So over here, I'm going to get rid of this gain because we're replacing it with our gen, right? Yeah, I'll answer this question about params in a second. We'll connect from the outlet of the saw into the gen inlet 1. I'll make this big as well. Cool. So we'll take the inlet here and send this outlet of the saw and the inlet into gain, and then we'll take the outlet of that and send it into the DAC. And one thing about the DAC is there are 2 channels because it's stereo. So we'll just send the outlet of our gain into both the first and second channel. And something you'll notice is if you hover over the inlets of things or the outlets, you'll get some tooltips about what they are. So that's a handy thing to be familiar with. Cool. So here I'll also connect it to my scope so you can see how it's getting bigger in my spectroscope, just because it's nice to visualize here. Cool. So the other thing we've got here is how do we control the actual parameter? Because right now nothing's coming out of our gen object here. You can create what's called an adder UI or a true, and you can click on it. Well, you can click on it and find your parameter that you've named. In this case, I've called it gain. And in this case, right now, my parameter defaults to 0, so there's no gain. So it's just multiplying our input signal by 0. But if you click over here and start increasing, click and drag, you start increasing your gain. And you'll notice that when I go into negative, the parameter is smart and it interprets it as a positive value. Which actually, okay, cool. And so another thing is if the farther right you click and drag, the smaller the increments go. So be careful as you're doing this. Sorry about that. Okay, so the one thing that maybe you'll notice is, okay, so I've got this gain, but maybe I want it to be in the scale of decibels instead of some absolute attenuation. And another object that is, an operator that you can use here is called A2dB. And this converts a linear amplitude into a decibel value. And so in this case, our parameter gain is coming in as a linear value, but you want to, maybe you want it to be in decibels instead because you want this to be like a gain object that you're used to. And so all you have to do is reconnect from the output of the parameter of the gain into this 8 dB and then send it back into your gain. And now we can see when we're over here, we'll be able to use values we're more used to with the gain. So like -60 will be very low. Oops. Yes, okay. So the problem is the defaults for parameters are from 0 to 1, and it's wrapping it improperly. So we need to tell the parameter what our default value is and what our min and max is going to be. So in this case, I'm going to say that my default gain, I want it to be at a very quiet volume. So I'm going to say it's -70 here. Is it common to have our oscillator outside of the gen patch? It can go either way. You can build your oscillator inside of gen or not. For this case, I'm just trying to get through the different very basic things with parameters. So I would say it's common to have it one way or the other. So so back to here, in the parameter, you can send the first initial value, and here will be -78 decibels. And then we'll give it what are called attributes. And these attributes that I'm going to give it are the minimum and maximum. So to do that, you do an @ sign, and you give it min. As you can see here, it specifies the minimum value for the parameter. Incoming values out of the range will be clamped. Perfect. So we don't want it to go outside of -70 for a minimum, and I want a maximum value. And for now, I'm going to say I don't want it to go above 6 decibels. That's like a pretty common gain slider maximum. Cool. So now this should be acting more as I expected to. I'll put it down lower here. Sorry. Here we go again. We're learning a lot here. So we're going from dB to A because our input is a decibel and we want it to be an amplitude. Well, let's try again. There we go. So now we've got our gain. It's starting at the lower you go down. This is -70 decibels. You can see there's still a little bit of something going on there, but as you go higher, it's acting more like a gain. Cool. So one more thing to notice from this getting familiar with the gen patch is that we still have this in value. This is like in a default gen patch, you start with 2 inlets and you get an outlet, but you don't necessarily need to have all those things. And in this case, I only want 1 inlet, 1 outlet. So I can just go ahead and delete this. And when you delete it, you'll notice that the outlet also dynamically goes away as you're doing this. Parameters are not inlets. They all can all be sent through the first actual port here of the object, and they go through these outer UIs. One thing to note about parameters as well is that they don't get updated as often as signals. So if you want something to be updated on every single sample, you're going to want it to be an inlet. And if you don't mind that it gets updated every block size, so maybe every 64 samples or however big your max vector size is, then you would set it as a parameter. Cool. So I'm going to save this, and I've got my first gain. Cool. So I'll close this. And another thing to note is that if you need help with things, besides the drop downs as you're autofilling things, you can find documentation for Gen in that same location that I was sharing with you before. This very first this documentation, all the documentation on Gen, you can find here online, but you can also find it within Max, and I'll be showing that as we go along as well. Cool. So now we're going to be going through here some of the more getting through different levels of practicing with block diagrams. So we'll start out with some more simple projects, some more simple block diagrams, which are home filters. These will help us get familiar with delays, how to handle feedback loops, do more practice with setting up parameters and inlets and outlets. Then we'll get to a biquad filter with some more, which is just a little bit more complicated because it has a few more sums. You'll learn a bit more about the feedback loops because there'll be more than one. And then we'll get into a flanger phaser. That'll be cool because we'll start doing some internal modulation of the delay loops. And then we'll finally end up with a reverb, a freeverb implementation, which will have some abstractions because we'll have some serialization of different filters together. And that'll make more sense as we start looking at these diagrams. So don't worry if that doesn't make too much sense right now. So for level 1, comb filters, we'll start out with this block diagram here. And so one thing you might wonder is, well, where do I find block diagrams in the first place? And usually it would be if you're working through a DSP textbook, there might be these kinds of block diagrams. They might be in white papers you're reading about new designs of filters and so on. And most of the examples that I'm going to be showing are from the Julius Smith books. If you click on, once I share these slides, if you click on all these images, it'll take you to their sources. And in this case, most of these are going to be coming from the Julius Smith textbooks that are freely available online. And I'll open up this patcher, the first template patcher that we're going to be doing here. And you can also get to these diagrams by clicking on these boxes here, and it'll launch the browser as well. So you should have this template starting out here, and I'll have everything in Max set up for you, as I mentioned. It has, it'll have an input noise. This is just some white noise going into our filter. This gen tilde will be our gen comb feed forward. And at the end, it's showing a spectroscope object, so you can see what the frequency response is of this filter, or rather the spectrum of the noise going through the filter. Cool. So once again, I'm going to unlock my patcher and hold down Command and double click to get into Gen. And in this template, I've already set up for you some the inlet and the outlet, which is a pass through right now. And these are the different objects that we're going to be using. We're going to be using a parameter, a delay, a multiply, and an add. And that's all you need for this implementation. So the first thing to do is that I like to do rather is set up all my parameters first, so I know what things I'm going to be modifying from outside of my Gen Patcher. And in this case, when you're looking at this diagram, you'll see that there are a few places that you can add some input. And by this, I mean there's this B naught here, which is taking one of the inlet signals and multiplying it by some value. That's what this triangle is showing. And then again here, coming out of this node, there is another multiply going on with B sub M. And then you've also got this box here with the Z to the negative M, which is just saying this is a delay of M samples. So in this case, M samples is going to be one of our parameters as well. So we'll have three parameters here: B naught, which is one scaling factor, B sub M, which is another scaling factor, and M, which is the amount of delay we're going to be adding in. So the first thing I'm going to do is unlock my Gen, move some of these things out of the way, and create all my parameters. One thing you can do, if you'd like, is to do Command or Control D, and it duplicates things that are already existing in these patches. So that might be something helpful as you're going through it. But for now, I'm going to first set up my correct one before I start duplicating something that's not even useful, because I don't need a foo parameter. I want a B0 parameter. That's going to be my my first one here. I'm going to set it to be a default value of 0. I'm going to say nothing is going through this loop. I'm going to set it just to be a min of 0 and a max of 1 in this case. And usually when I'm doing, if there's nothing given in the paper anywhere about what is being, or like what the range of a multiplier is, it's usually a 0 to 1 because it's some kind of attenuation. So it's like, it'll go down to amount of zeros passing through or the entire signals passing through. So that's a general default that I go with when I don't have any other information about a block diagram. Cool, so we've set up our first parameter here. I'm going to duplicate it like I mentioned. You click on it and you do Command or Control D, and you've got a second copy. And all you need to do to make the B sub M is just change the name of it. So I'm going to be using the same default and same min and max. Another thing you can do if you'd like is make them a little narrower just to fit on your zoomed in screen. And copy and make our final one, which will be this delay amount. And instead of calling it M, I'm actually going to call it delay in this case, just so I am a little more clear about what's going on there. Cool. So I've set up all of my parameters, and I'm going to now take a bit of a step here and go into my host, into my max patch, and create my adder UIs so that I can control those parameters again. So one thing you can do is create a new object and say N and type in adder UI, or I'm going to delete this. You can just hit the key A and it automatically create one for you, which is pretty handy, especially if you're using lots of parameters in your Gen patcher. Cool. So we've created one of these, and we're going to connect it into Gen. And since there are 3, I'm just going to hit Command D and duplicate it 3 times, or rather duplicate it twice, so that I have three of these objects. And connected it. Cool. I'm going to select all the different values. So B naught, EM, delay. Perfect. And one thing I'm noticing now is I've called the delay 0 to 1 because I've duplicated it, but that doesn't make too much sense for a delay because the delay is going to be an integer, right? You're going to say, I want to delay it, I don't know, maybe 20 samples. So instead of having a max of 1, I'm going to give it a max of, let's say, let's try it to 200 here. Also, a delay of 0, I don't think we're going to actually want that to be our default. So I'm just going to say a delay of 1 sample for now. Is there, oh, sorry, thank you for reminding me of this question. Is there a difference between capital param and lowercase param? Nope, there's no difference. They're exactly the same. It's just a preference of what you like to see. I tend to use the capital because it is the first autocomplete suggestion. Cool. So now we've got our parameters all set up and they're hooked up in our outside patch. So now we're ready to start doing our prototype here. And the next thing we'll see is we have these other objects that we have instantiated inside of our gen. There's going to be the sum we're going to need to do. We're going to need to actually have the delay. We already have the inputs and outputs. So let me first disconnect those because in the block diagram, they're not connected. Cool. So what is easy to do is to, or rather not, maybe not easy, but a handy trick that I've been taught is that if you think about a block diagram by turning it 90 degrees on its side, that's a very helpful way of looking at it in Gen, because in Gen you're going from top to the bottom, and in block diagrams you're usually going left to right, or sometimes right to left. So mentally, you can kind of turn it to your head sideways, but I usually don't actually do it because then I can't read the text. But if you find that helpful, I'd recommend taking a screenshot and rotating it. And actually, I'll do that just for this purpose. Here. You can think of it going like this. 90 degrees, make it smaller for you too. So what'll happen is we're going to have this input at the top. We're going to have a delay, a sum, and an output. If that's helpful for anybody, I would recommend trying that on your own. Cool. So going back to our patch, let's get to it. So first, I'm going to set up the sum because that's nice and big and a meeting point for a lot of different connectors. So I find that helpful to have all of my different objects set up ahead of time. Because as I mentioned, most of what Gen is not so much the objects, but the connections between them themselves. Then we see we have this delay here. So I'm going to put that above the plus because it's to the left here in this actual block diagram. This multiply is going to be near our 2 parameters here. It's going to be near the B naught, the B0 parameter, because we're going to need to multiply it. And then we're going to need another one by our B sub n because we're going to be multiplying that. So I'll duplicate it and put it here. So now we kind of have a little bit of a sketch of what's going on. And so, well, what do you do now? How do you do the connection? And this is where it requires the most kind of thinking, but it's the meat of what we're going to be doing. So the first thing is there's a bunch of paths through a block diagram. When you start from the left, you can start following it and you get to some connection point, you get to some node and you see, I can go at this particular point, I can go one of 2 ways. I can either go into this delay operator or this delay node, or I can go out this direction and go into this attenuator. And so one of the things you have to do is decide, well, okay, which way makes the most sense to me to start thinking about the connections. And for me, I see that this attenuator here that bypasses the delay in these other attenuator, that it's easier to just go this direction to get closer to the end. So I tend to take short paths to the end before getting into the more complicated ones. So that's what I'll do first. Okay, so we're going from this inlet and we're going into a multiply with the B naught. So how do you do that? Well, it's sort of like the game we were doing. You take the inlet and you go to a multiply, and then you want to multiply it by your parameter. And so now we've created this node, which is in effect this node. We have this connection going, we're doing a multiply. And then what happens after you do the multiply? Well, it goes into this sum here. So what you do is you take your multiplied value and you go down to your output. And so now we've followed this entire path here. Perfect. So now you go back to the beginning and say, well, I haven't covered all the different paths I can make. So what about this one here? What if instead of going out here, I go through a delay? And so the way to do that is you take your inlet, you go into your delay and connect those two. And so how do you actually set the delay? Well, that's what this second input is. And if I hover over it, it might be too small for you to see on my monitor, but on your screen, you should be able to see it says set delay time of tap 1 from 0 to 44 100 samples. So likely your sampling rate. And so to set that, we have our delay parameter already. I'm gonna stick this over here, try to arrange things so that it's visible. And you can even drag it out here. So it's a little more space. And you connected in your delay. So now you have, we're going through this path, it goes through the delay, and it's a user set amount of delay. And once you go through the delay, then you're getting to this other attenuator here. As you can see, it's another multiply. And so we'll connect from the delay into the multiply. And again, we're going to be using the input parameter to tell us how much to multiply by. And I see now I've noticed that after the multiply step, the attenuation, it's going to the sum. And before, I was immediately going to out. So this was a mistake I made earlier. I meant to connect it to this sum. So now, going back to where we were, the attenuation from the B sub M section, we're going to be adding in with that original one. And so after this sum, we'll go to the output. Cool. So I'm going to clean this up a little so it's a little more like the shape of the block diagram. Oh, that's good. Good for me. Another cool thing you can do to clean up your patches is to click on a patch cord and right click it, and you can say root patch cord, and it'll immediately create bendy, straighter patch cords so they get out of the way of each other automatically, which is kind of handy. If you ever want to remove it, you right click and you say remove all segments. Cool. So just to recap, let's check that we've done everything right before we turn this on. There's no audio actually to our DAC here. We'll just be looking at it here so I don't send too much white noise through your speakers. But just to check, remember we've got an inlet. It's going 2 different places. The first one is through to this attenuator, the B naught, and then it's going to a sum. So here it's going to the attenuator, it's going to the sum, into the output. And then the other path, you go into a delay, an attenuator, a sum, into the output. So we've done the delay, the attenuator, the sum, and the output. So it looks like we're okay, but let's try, because compiling on the first go can be tricky sometimes, even if it's just a patch. Cool. So once you start playing with these parameters, you'll notice that the min and the max, when you're dragging in the adder UI, it only lets you go as far as the min and max, which is great because it'll keep you from blowing up things if you set your min and max properly. Well, so if I set my, let's try and figure out what these do. What's fun, or depending on what your definition of fun is trying to figure out what these actual mathematical values are going to do to your output. So what's kind of cool here is you see that, oh, if I set this attenuator to 0.2, these are kind of making some effects, but the more I change the delay, that's really where you start to see what the signal looks like. So the smaller delay, the farther apart these different, the different parts of the comb actually are. And you can see right away what happens when you start changing these values. And perfect, you've made your first comb filter, a feed-forward comb filter. These are super useful, and we'll get back to using comb filters later on. They're all parts of reverbs and things like that. So even knowing just how to do this in your first, I don't know, 15 minutes of actually patching this thing is super cool, I think. Cool, so I'm gonna save this so I can go back to it. But as I mentioned, you can go through to the solutions and you can see the end results as well. Awesome. Okay, so now we know how to do a feed forward because it's going forward. That's why it's called a feed forward filter, because you're going to the right, you're going forward instead of reversing from later on and going backwards. I don't know if any of those words just made sense. But now we're going to try a feedback filter. And again, this is from Julia Smith. It's a great resources for doing your first block diagrams. They're very clear and they explain it as well in mathematical form below them. But anyway, so again, we're going to do a feedback filter. And we're going to see what does this look like as opposed to the feed forward comb filter. So let me grab our template again. I'm going to go into our patchers here, and I'm going to start with the feedback patcher. Let me move this out of the way too. Don't like that it's back here. You can see it as well. Cool. Make this big again. Drag it out for you. Okay. So again, we're going to be starting out with white noise, so it'll fill the spectrum. And we're going to start adding into it as we start, we'll start adding into it as we're working through this diagram again. Let me turn it off while we're just patching. But of course, you could leave it on and see what happens. Maybe you'll get something kind of cool. You know what, let me do it too. It'll show you what it looks like as you're patching. Things will change as you go. So once again, we're going to want to start with parameters. Find that's the best thing to do to start with. Zoom in here. Okay, well first I'm going to get rid of this pass-through, so you're not going to see anything coming through the spectroscope. So you can see how quickly that happens. Immediately to delete it, right away things go. And actually another thing I can mention that might be useful to some folks is there's this auto-compile feature. Maybe you have a huge patcher, like you can get to really big gen patchers and it starts to take a little bit of time to compile the actual generated code that's within here. And it's like slowing down your workflow. So maybe you want to turn off this auto compile for a while. So while I have this turned off, watch as I disconnect the inlets and outlets and nothing is changing because nothing's been recompiled. So that's something to keep in mind as you start going forward. But I'm gonna leave it on because we're not doing anything super intensive right now and it'll be cool to see as it goes. Cool. So as I mentioned, let's start with our parameters, and it'll be very similar to before, except it'll be named slightly different. I can already see there's this -a besides the B not and the N. So let's go over here. You know what? Let me also show you that if you go from one patcher to another, you can actually copy and paste from one patcher to another. So we're gonna make things faster for ourselves and grab the delay parameter and the delay and the B naught parameter, because here in our feed forward, these will be the same. So to do this, I'm unlocked. I click one, hit shift, and click the other. So like maybe you're already familiar with that with most applications do this kind of thing. You can also do like lasso select. You grab a bunch of things and you can keep shift and disconnect wherever you want. So anyway, so I have these two selected. I'm gonna do a Control C. Open up my feedback patcher and copy in these parameters. And we've already got them. And because I have auto compile on now we're seeing that things are disconnected. Cool. Okay. So let me close this, just to show you that you can easily start from one place and avoid duplicating efforts if you don't need to. All right. So we've got our V naught attenuator value. We've got our delay value here. And we're going to want the A sub M value. I'm not going to include negative in the name, and that'll make a little more sense when playing, because if you think about it, when you're working as from the user perspective, you probably want to just think about changing a sub m. It doesn't make too much sense to say, oh, I'm going to change negative a sub m. So that's kind of my thinking of when I'm choosing parameters. Okay, so a sub m, I'm going to have this parameter. Again, it's an attenuator, so I'm going to give it a default of 0, because that makes the most sense to my brain. And I'll give it a min and max again, 0 and 1. Min, max. As we saw before with the game, the min and max default to 0 and 1, but I think it's nice to have it explicitly set. It's just, in my mind, it's a little cleaner and it's a bit more obvious what your intents are. Cool. So once again, we'll see where our major operators we're going to need to set up are. So once again, there's this summation that's going to happen. So we've got our sum that I've already set up for you, the delay, which is here, and we're going to need some multiplies for our the attenuators. Okay, where do we start? Which path should we take first? Well, I think it's pretty obvious here because we only have one to choose. Our inlet goes into this B or B naught attenuator. So let's set that up first. We'll take our multiply, and it's going to be a user supplied value multiplying our inlet. Cool. That's pretty easy. I'm going to draw this out because it'll be nice to have things lined up. Visual sake. Okay. And so now once we went into the attenuator, we're going to hit this summation. So let's drag our summation right after there and connect those two. Okay, so now this is where we'll make some decisions. And you'll notice that technically this is another connection we can follow, but it's facing the other direction. And I find it's better to follow the arrows, follow the flow of the signal rather than try to just look at the actual connections. Following the flow makes a lot more sense, especially when you get into deeper nested things that we'll see a little later on. But for now, you can take, I would say, take my word for it. So next, we'll decide there are two options. Well, we can go into this delay or we can go straight to the output. And I say, why don't we go straight to the output first? Make sure we get that connected. And so nothing's showing up here yet because, again, our attenuator is 0. So let me take this as an excuse to set up our parameters, which maybe usually I would have done a little earlier, but I got excited by copying from one patch to another. Okay. M, B0, and 11. Okay, so if I turn up M, it should do something. Oh, no, B not. Perfect. So now you can see that this is all set. Now we'll be able to see things change. Nice. Okay. Getting distracted here is good. Okay. So after the sum, we went straight to the output. But what about our next path? That'll go into a delay here, and then I'll go through some more of the path. Before we think about that, let's set up the delay. After the sum, we're going to want to go through this. So another patching trick is to, while you're selecting it, hold down Shift, and you can drag right over a patch cord, and it'll add in. And you can also shift and drag out. And I find that's a super handy thing as opposed to like clicking on a patch cord, dragging the end and putting it in. You can just do this. Is it possible to set delay parameters to int only? Oh, so you mean here if you are, how it basically does a floor here. Unfortunately, you can't do that, or at least that I know of. It basically truncates for you ahead of time when it's sending into the delay. Or well, you're obviously not seeing anything here because I haven't connected yet, Isabel. What am I saying? Let me connect it and show you what I mean. You can see that as I change this. Well, actually, rather, this won't really show you very much, but Is there a way to show this? I don't think there's really a way to show this, but no, there's no, there's no way to set it to be int only, unfortunately. If you do want to ensure it inside, you can pass it through an int block, or I believe there should be a floor. You can round down, or there should be a ceiling. Yeah, you can do a floor or a ceiling. But yeah, the suggestion about using an int block is also a great one. But it automatically will truncate it here when you connect it with delay. Okay, so we've got our delay connected. And I'm gonna disconnect again because I don't want this. Oh, Isabel, what did you do? I disconnected this. I'm gonna reconnect this. This was our original thing. If that makes sense. Okay, so the other direction out of the sum, you were going through the delay, right? Okay, perfect. Yeah, when you depending on when you click and drag in this adder UI, the farther to the right, the smaller the spectrum. You can actually make it quite big if you want. Drag it, and you can get really precise if you want. I'll leave that, even though we're only going to be wanting to do it. Anyway, okay, so back to the delay. Once we're outside of that, we're going to go into another attenuator. Got our AM parameter. We want multiply, so duplicate that. We'll go outside and take the outlet of the delay, attenuate it by AM, and it goes back into the sum here. So we'll notice, just do this. Perfect. And so now we've got this kind of wonky feedback loop is going through. And you'll say, okay, maybe this looks a little kind of confusing. One thing you can do is do the route flashcards I mentioned before. That kind of cleans it up a little bit. Okay, so now let's see how it's going. Let's lock this so I can adjust values. See what happens when I'm doing the feedback. See if I did everything right. Aha, okay. What did we do wrong here? Well, this is a negative a sub m. So instead of multiplying just by this value, we've got to say, well, am multiply this by -1. So in here, I'll create a new object. We can do multiply. And then instead of taking an inlet, you can also specify it directly inside the lock. So I can just say multiply -1, and it'll multiply my parameter by -1 here. So let's see how this goes. Yeah, this is looking a little better. You can see it's doing the peaks as opposed to, yeah. Cool, so you'll notice in this comb filter, you start getting the feedback. It gives it a little bit of a different shape. It's a little hard to tell in the spectroscope because of the what's the word I'm looking for, resolution of it. But you do get the general picture of the shape. Yeah, there we go. Cool. So now we've got our feedback comb filter. Let's save this and head back to our set of examples. Okay, so here we are. We went through our feedback comb filter, and now we've reached past level 1, and we're on to level 2 of practicing with block diagrams. And as I mentioned before, a biquad filter, you're starting to get a little more complicated with things. And maybe you're wondering what's a biquad filter if you're not familiar with different filter types. But a biquad is basically the building block of most filters, of most IR filters, because they're very numerically stable. There's only two, there aren't too many summation points. You're not getting lots of like floating point truncation things. So it's very numerically stable. And in particular, there are a few forms of biquad filters, and this is one that'll be, this is one of the more stable forms of it. And so we'll go through this one. I'll talk a little bit more about it as we go through, because, let's see. Okay, so grab our patchers. We finished our comb filters, and now we're on to patch 3, which is our biquad. And so, as I was mentioning, there are a few forms. there's this transpose direct form, which is the name of this one. And they're also just direct forms. So when I launch this, you go and look at what Julia Smith is talking about. You can see there are these other shapes here. And when we open up this patcher, I have this example here. And there are a set of Gen factory examples. There are a ton of them, and they're very useful to go through as you're trying to practice more. Maybe after this workshop, you want to go and practice with some more things before you go off on your own. And the place for those are inside of the Max. You can find it under help and examples. Then in here, and specifically within Gen, you can just see like the wild number of things you can look at and kind of look at how these things are done. And so in this case, I'm loading a factory example of the Gen biquad. So we'll take a quick peek at it. And so this is the Max patch, but inside of Gen, you'll notice, hopefully you can see, this is a direct form of the Pole 2.0 filter, which is a biquad. And so the reason I decided to show you the transpose direct form to practice with that is to leave this as an exercise for the reader. If you'd like to look through this and see, well, how's it made? Like, try to match it up to with one of these existing diagrams. That's basically how I've gotten more comfortable with Gen as I've been working with it, my own practice. So yeah, that's a bit of an example, and I have this that loads the factory example. So if you would like to try that yourself, you can go ahead and do that after this workshop. But yes, okay. So we've got our biquad here, and we're going to go and try to build this. And I'd say this is our next level up because, as you can see, it's a bit more complicated. There's more route to choose from. How do you like keep track of what you're doing? What is this? What is this talking about here with the S2? Is that something we need to do? So this is our next leveling up. Okay. Let's see. I'll clean things up here for you. So yeah, to recap what I just went through there is examples are great. You can find them in Help Examples Gen. You can also find this particular one here. Would highly recommend. Okay. So to dive into this one, let's open up our template. Here. And you'll notice that I've added in a few extra template things here called history and this minus. And as we go through, you'll see why I have those added in. So as always, let's start with the parameters first and drag this slightly off screen so you can see both things going. I'll close this one over here. Cool. Okay. So let's do parameters as I mentioned. I'm going to just type them all as we go, as opposed to pulling from the other examples, just because I'm going to start from a cleaner slate, I think. Okay. So look at this diagram and see that there's a bunch new attenuators. There's -1s as our delay operators here, and a few more inlets now, or sorry, a few more summations going on. So what do we pick first? Well, I'm going to pick the attenuators because that's usually where I start. See, I like working from top to bottom if I can help it. So I'll do B0 first. And again, all these are just going to be default to 0, and then 0, max 1. I'm going to duplicate it. Just rename this one 1. This is B1 next. You can go left or right, but I'm just going to do B2 because it kind of makes sense to say 1, 2. Drag this out of the way again. And I'll just drag 2 of these and duplicate both of them. A1. B2. Cool. So I've got all my parameters set up, and just so if you're working along, you can do this too. I won't be able to see it as we're going because I've got this on my screen this way, but set up your parameters outside as well, so you can play with them as you go along. Duplicate. So I've got all those parameters set. And let's look through here. Did I miss any? Well, these are all going to be -1. They're just single sample delays. So that's not going to be a user editable, usable, modifiable parameter. This S2 is actually just naming the signal here because you can tell because it's S2 of n. That's telling you that it's a signal, sort of like how it's X of n or Y of n. And then again here, S1 is a similar thing. So it looks like we've got everything covered. And if you're familiar with biquads, maybe from the default biquad object in Max, because there already exists a Max biquad. We're rebuilding ourselves, as you can tell. There's these different feed forward coefficients we can give to this biquad filter. That's just an aside for you all. But yeah, okay. So we've got all our parameters set, and I validated that that is true by seeing that there are those same inputs of the real biquad, or the quote real biquad of MSP, Max MSP object. Okay, so parameters set. Let's find our our operators to add in here. So we've got 3 adds that we're going to have. I'm going to take this and line them up instead of up and down. I'm going to do them left to right. Hopefully this will match up pretty well. Okay, so we're going to focus again on the inlet first, and then deciding which ways to go. As you can tell, there's sort of this process is pretty easy to replicate with different diagrams. So we get to this first node here, and we say, okay, we can either go into this attenuator B naught, or we can go down here into this more complicated bit. But as you can tell, it goes. This one is a shorter path to the end, so I'd like to do that first. So we're going to attenuate by B naught. So let me grab my B naught parameter over here, resize it because I like that. Grab, multiply to attenuate. Connect together. Inlet to that attenuation. And then after attenuation, it goes into the sum. Put the sum here. We disconnect this guy because that's not right. And connect from the sum to the outlet. Cool. So why don't I line this up? I feel like I spend a lot of time lining things up because it makes me feel nicer. But I think it's good practice to do that. It stays a little cleaner. You clean up as you go. Okay, so we made this through this path. Let's figure out the next path. Pick option 2. So we'll go down and we get to another node. I'm going to pick what looks like the shorter one here, which is going to be B1. Grab B1, take multiply, maybe it's that one. Multiply, parameter. So again, where did this come from? Well, it came from the inlet. So we go here to here. Cool. And then after it's been attenuated by B1, that's what we just did, we're going to go to a second sum. This is not the one we already had, so we're going to have to, that's what this little operator comes in. And so that is going to be, oh, another thing is that it doesn't really matter which inlets and outlets you put into a plus sign, because the thing about Gen is everything gets summed into a sum. So if you're putting tons of inlets into a plus operator, let's pretend that these are actual things to connect, it'll sum all these values. So that's just to mention anything, if you have multiple things getting sent into an inlet, they're all going to get summed before you do that. So keep that in mind. If something wonky happens, maybe you've connected something incorrectly and there's summing and you're not really expecting that to happen. But yeah, that's why I connected and was like, that's wrong, but really, it really didn't matter which one it was there. Cool. So we've set up this sum after our B1 attenuation, just to get back on track here. We've hit our sum, and now we really only have one direction to choose because everything else is coming in here. We need to go to this single sample delay. And I quickly mentioned this when we opened up, that there's this new object that we'll use here called history. And history is just basically like an alias for a single sample delay. So if you ever see a z to the -1, that's basically, you can immediately think, okay, that's a history operator. Cool. So we send here from this sum into the history. And after this history, we're going to send it back into the first sum. And so that's this one here all the way on the left. Click. And it doesn't matter, like I mentioned, doesn't matter which one you want to put it in. And so I'll just pick the first. Okay, so now we're hit the sum, and we've already made this connection here. We've already made the connection to the outlet, so I'm going to leave that for now. Okay, let's go back to the inlet and work on this last connection here, because we were working down this way. We hit this node, we went this way already, but what if we go this direction? Well, we're going to need a third sum. So we've got a third sum here. This will happen after we attenuate by B2. So we'll take this parameter, and multiply. And we need the inlet. So where do we start this connection from? Well, it's the one that comes right before B1, or rather, it's just the inlet. So we'll say in. That's being attenuated by B2. Besides these, let's put together. Okay, so now we've hit this B2, we've attenuated it. We've taken it in that, we've attenuated it. Now we're going to go into this sum here. So we go B2, sum. And then what happens after this sum? Well, it goes into another history. So let's duplicate this one. Connect. So we've went through B2, we've summed it. We're going to add it to the history. That's going to go back to this second summation here. So let me connect it over here. So history is like delay, but it's just a single sample. So it's like if you had delay 1, basically. Yeah. So yeah, so if you have z to the -m, you use delay. Z to the -1, usually you use history. Don't have to. Cool, so now we've hit here, and we've already handled this flow to the outlet. Okay, so we've done all of our B2 attenuation. These are all our forward tasks. We're just going straight to the outlet. But now you notice that we didn't take these paths yet. After this final sum here, which corresponds to this object, well, you could also go back into these other two sums. We can go back either to here, or we can go back either to here. So let's handle those. We can make this a little taller, maybe. That should give space. Okay, so after this sum, it's this one. We're gonna, why don't we take this path first? The attenuate by -A1. So we'll take A1 parameter. We're gonna want to multiply it by -1. So multiply inputs, -1. And then -1 attenuates this output here. So do that. So next the sum, attenuated by -1, and then it goes back into this second sum here. So if we follow our paths carefully, this was the second column here. This was the second row. So this looks to be the right one, right? Because it was attenuated by B1 and it was getting added. So this looks right. So we're going to take this, we'll add it to this sum. We're starting to get a little bit crowded here with the cables. So let me clean up by doing some routing of the patch cables. And one thing that's a handy way to do is if you're on Mac, you can hit Alt and drag, and it'll click, select all the cables. It'll select all the patch cords, or rather select patch cords and objects. I think it's Option on Windows. And so once you have all of your patch chords selected that you want to route, you can just right click and do route patch chords. And it'll be a little cleaner then. Let me do this one as well. I tend to do this quite a lot because I find it cleaner, and some people might not like it, so you don't have to. Okay, so where were we? We were attenuating negative A1, and it was going back into this sum here, and we already handled that route, so we're good. Okay, so we're on the final step of this biquad. And to do that, we have to take this final route here with a negative A2. So you kind of see the symmetry here, which is kind of cool, I think. Multiplying by negative A1 in the attenuated signal. So I'm going to select these and duplicate. Grab them like this. Okay, so where does our inlet and what is our outlet to A1? Well, it was this last place we came out of was this kind of main sum here, which is this one. Click it and drag, click it and connect. Okay, so we've got our inlet to negative A2, and then we've got to connect this one to this third sum here. That was the one that's here, and it was connected to the outlet of the attenuated B2. So connect, and it's the sum. I'll just use the first one here. Okay, I'll route these because I like that. And should we go through our patch again to see if we're connected correctly, or just go for it? I think we should just go for it. No audio connected out, so we won't be hurting ourselves here. Okay, so don't see anything yet because all of these are 0. But let's try changing some values. You see their signal. And so these values won't make too much sense because trying to change these values won't make too much sense here, because you're not like changing like a filter graph or something where you're like dragging a low pass filter. You're literally changing the coefficient values. If you wanted to actually calculate what the coefficient values are based on, like, say you want to know your feedback, your Q value, say, or you want to change your cutoff value, you'd actually have to compute which of these will work. And so there's a few ways you can do that in Max if you want to play around with it. There's also, in this example that I showed here, there's actually already a tool to help you calculate them within Gen if you'd like. And that's really useful if you're using it as a building block, say your own like Gen biquad. You might be using it in some more complicated thing. You can go here and just immediately grab what's going on in this patch here. So I can point you to this as a place. It'll do the calculation for you. And you'll notice that in this example, it'll show you what I was talking about with CodeBox, which is this Lua-like language, which is called GenExpr, the GenExpr language. That's sort of outside of the scope of this workshop, but you can learn a lot from the examples to learn about it. But the point being here is this is an example of what CodeBox looks like. And it's pretty useful for calculating things like these coefficients because it's straightforward to just write, find the square root of this value, and then 1 divided by this value. It's in some cases it's easier to just see it as a code box. But long story short, you can just grab this whole thing if you wanted to create to calculate the A and B values, for example. And if you're very carefully watching along, you'll notice that actually as a side note, is a different filter, depending on how you see diagrams. Sometimes biquads are labeled, the B's and the A's are switched. So if you'll notice in here, and you try to go and copy this in your own examples later on, you'll notice that there are 3 A values and 2 B values because they're switched. So just keep that in mind if you do go through these examples and you're wondering, why does Julie Smith use these values and this example uses these different values? For a start, like, for why the case is different, particularly here, is because the maximum implementation of biquad calls them A and B in this order. So the B naught here is an A naught. Long story short, there's kind of no better way. It's kind of half people are in one camp of liking A's and half like B's. So just as an aside of if you go into these examples, you're after this workshop and you're looking at the examples and you're wondering what the heck is going on here. That's kind of why. Cool. So we've got our bipod working. And one thing actually I can mention here is that in this case, these coefficients don't actually have to be 0 to 1. They can actually be negative in the case of bipods. So let me just, for an example, let's change these to min -1, say. Just change a few of them so you get the idea for it. And that, if I'm remembering my GSP correctly, once you start getting negative values, you can start getting different shapes. You start going from low passes to high passes and so on. And so see, cool, I'm making what maybe is some band pass, something like that. But yeah, so once again, I kind of nerd out about, I like the fact that I can play with the real parameters that are in these diagrams and see what's going on. And it gives you kind of a cool experience. Yeah, so that's our biquad. And I'll say that that is good for level, what level are we on? Level 2, right? Let's see what I labeled this. Yeah, level 2. And I see that we are halfway through our workshop. I can use a drink of water. So I'm going to say, why don't we take a 5-minute break? I'll answer some questions in the chat if anybody has them. And then we come back for level 3 and 4 before we move on to the exporting sections as well. But yeah, so there's a question here that just came in. So far, Gen is like P, which is a subpatcher, except it only accepts and sends audio flow and has predefined DSP function and also precompiles independently from the main patch. Yes, that's pretty close. I would say it's more like, I would say yes, but the closer thing to think about is it's a self-compiling object. So if you've ever written max externals yourself as like an MSP object, it's more similar to that. You're defining the attributes you can have, you're defining the parameters you can send in, and you're within like a gen patch or like a patching environment, you're creating the perform routine, basically. Everything you're seeing there is what'll happen within like process a block or something like that. But yeah, that's true that it only accepts and sends audio flow, a gen tilde object that is. There actually is an event rate gen that we're not covering here. But it does have some predefined DSP functions. And precompiles, yep, that's also true. Cool. And so then is gen not gen tilde performing operations that sample time for non-audio signals? No, it performs at block rate. It's basically like a self-compiling max object. I feel like it's very useful in very specific instances. I actually don't know what I personally would use it for, but there are some examples in max in the examples section of gen that show this. They're usually just like, see, they're mostly gen tilde. There's also like gen MIDI LFO. I believe this one. Yeah, this is an example of what it is. So I'd recommend looking at this example maybe, as well as the gen overview here. It talks about the differences between, there's gen event rate, there's gen tilde, which is the MSP version we're looking at, and there's also a jitter gen. So if you are jit.gen, so if you're working with jitter and you want to do single like sample rate like shader type things. I don't use jitter too much, so I won't say too many things there. But basically, yeah, there are different versions of gen. That I should mention that as well. Okay. Yeah, it is good for me. Let's see. Okay, so where did we just end off? We ended off with a biquad, and we're on to level 3, and then we'll get to level 4, which is our the final boss, right? Okay, so level 3 is a flanger, and so in this case, I've actually taken this this image from MathWorks, because they have some nice delay-based audio effect diagrams here. I think it was from their Simulink, maybe, I don't know, not too important where the context in MathWorks, but yeah, this is where I got this diagram for. Sorry from. And we can look at it in a little bit larger form here. And the reason that I would call this level 3 is that we're now introducing some internal modulation. Now we're not just doing summations and feedback, we're also doing modulation of the delay. Because that's basically what a flanger is. It's you change the size of your delay over time, and it creates that flanger phaser effect that you know and love from your guitar pedals. Okay, so once again, we'll start with our template here. Say flanger, and inside of this, I've got links to everything as well. Slide this out of the way. There we go. Okay. So once again, we've got our diagram here, our block diagram. There's a link to this where the diagram came from if you want to check that out, and try out other block diagrams on that page. That could always be another place to work on examples for you. And then again, I have a factories link to a way to get to an example of it from the factory example. So you can compare what you've done to, or we can compare what we've done to the built-in examples. One other thing to note here is there's this handy thing in Max that maybe even seasoned Max programmers don't know about too much. This is like a B-patcher. So a B-patcher is a UI subpatcher. So this is like basically an embedded UI that is made also out of a Max patcher. Anyway, to get to this, you would type B-patcher and you give it the name demo sound. And you get this really helpful built-in patcher that has a bunch of things that you can use for testing. I use this all the time when I'm testing effects because it's really easy to change whether you're doing from a sample, a sound file, an oscillator. It gives you a bunch of sample oscillators to pick from. You can sample noise. You can even sample yourself. I want to do that in case there's weird feedback. I'm not connected, so I shouldn't. But anyway, there's a bunch of different things you can test with here. You can use built-in Max samples, so you don't have to go digging through your huge sample library to find something that's good. You can just pick one of the Max classics, like Anton or all these different ones that you know and love, and it has gain and everything. Anyway, this is really handy, especially when you're working in Gen. You don't want to fuss around in Max to get things set up to work on. Yeah, so that covers most of this here, and so we can go ahead and work on our flanger patch. Once again, slide everything around and resize for you all. Okay. So, well, what do we do first? We pick our parameters. And in this case of the flanger, let's figure out what we want to set as a parameter. I know there's a delay, and this has some value. So, well, what do I want that delay value to be? That could be a cool parameter set. So let's call it here delay. And I'll give it a min value of 0 and say a max value of, I don't know, I'll pick 300 this time. Cool. Okay. What else is here? Well, there's this feedback loop. So what is the attenuation of this feedback? How much feedback are we going to have? That could be a parameter we're interested in. So let's call parameter feedback, FB. And for that, it's an attenuator. So let's just do 0 to 1. What else? Well, there's this modulator of the delay. Maybe we can change the speed of that modulation. So we'll just call it about, just call it mod. And you can say a speed of 0. This will eventually be in hertz, I would say. So let's go up to 20 hertz maybe. Mostly because this is saying it's an LFO. So I would imagine we want to keep it in a sub hearing range. Let me quick grab something on my end. make sure. I want to make sure I've got anything. Make sure I'm setting one thing up correctly first. I'm peeking, but you shouldn't peek at the solution. Well, okay, the one other thing that we're going to want to have a parameter for will make more sense when we're going through it. Okay, so for now, this is what we'll say. We have a delay value, we have a feedback value, and we're going to have this modulator speed. Okay. So we've got our parameters, hook them up in our max match. That's up here, A. Okay. Okay, so we've got our feedback, mod, play. Cool. Now, going through our diagram. You'll notice here that there aren't really any, there are no sums like there were in the Julia Smith diagrams, but you can notice that most of these connection points, that is essentially a summation point. It's a point where the signals merge and they get added together. So that's just a thing to keep in mind, because saying, well, what do I actually add in here? Well, I'm going to need to have a sum here where this dot is. I'm going to need to have a delay like I'm used to, and there will be a mixer, which is also a summation section. Anyway, so to start, we'll grab our sum, and that'll be our first inlet, and let's get patching. So inlet to this node, connection node here. And I see there's a really easy direction out to this mixer. And so there's a few ways you can go about using a mixer, because this is basically a dry wet control of like how much of the modified signal do we want to have in. So this is like basically attenuating how much of this pass through is and how much of this actual modulated delay we're going to be adding. And so there's a handy, useful operator that is a mix. And looking at what these different inlets are, you can hover over and say output if interp is 0, output if interp is 1, interpolation factor between inputs. So knowing what this is saying is like, okay, here's my dry signal, and this is like my wet signal, and this is the amount of mixing essentially. And if hovering over these doesn't really help, because it took me a second there to realize what is this actually saying, you can also right click on operators. I was doing this today, but you can say right click and either hit help or reference. I usually go with help because it's right in here, this drop down that you can't read on my screen, but you get this short reference that explains a little bit more about what's going on with the different operators. And again, this is probably more helpful for more complicated operators than like sum, because it's pretty straightforward what a sum would do. But in this case, it says it mixes, interpolates between inputs A and B according to the value of the third input T using linear interpolation. Okay, so that's what we were figuring out so far from the hover text. But also it gives us this information here. It says the factor T should vary between 0 for A, so fully this signal all the way on the left, and 1 for B, which is the second inlet. If one argument is given, it specifies the mix interpolation factor. So that's saying if I had started this mix and gave it a value of like 0.5, it would hard code in that I want this mix value to be like, I want the dry wet to be 50%. But maybe this would be a parameter that we want to specify, so I can just leave it as mix here with no argument added after the name. So while I'm doing that, why don't I create a parameter for it and say I'll call it mix instead of dry wet, and we'll go from 0 to 1. And maybe I want my default value not to be 0, and I'll make it 0.5 here in this case. Okay. Cool. And connect that in. And while I'm at it, let's add our UI. And connect it. You can see mix. There we go. back to our diagram now. And maybe just to remind you, that was a right click and hit help. And that's a useful feature. The other thing you can do is hit open reference, and you'll get a slightly larger window. And it's maybe easier to see or have off to the side. It's more, you've got all your inlets and outlets explained here. It also gives you a handy thing that says see also, and it tells you like which objects you might also be looking at. If you're in the headspace of thinking about mixing, maybe you want to use a gate, which you can select like binary between two inputs, or a selector, or sorry, select between different outputs, where a selector is number of inputs and things like that. And clicking on them will take you to the example or the documentation of those. Another place you can get to that is over on the actual patching window itself. You can click on an operator and hit this little panel button here, which is reference. So we'll reload it, and it'll show you the same thing. It's just a different format. If you like having it in the same window here, gives you the explanation of what's going on and the different inlets and outlets, and what you can add as the values as arguments here. Let me close that and get back to our work here. Okay. Okay, so we were saying input going into mixer, going to the output. So that was after our node here, the sum node. And we'll say that is our dry signal. So we'll put that in left. So that'll be when mix is 0, it'll be fully dry. And then after the mixer, we can set to the output. Cool. So now what do? We actually do, now we have to go do the hard work, right? Now we're going to go, instead of going straight to the mixer, we're going to go over here to this delay. So well, let's put it above the mixer, because the mixer will be pretty far down on our signal chain here. Okay. What is the purpose of passing through the plus node? What difference would it make to go directly to the mix node? That's a good point. Why did I do that? I think I was thinking of like if you like wanted to add some feedback to this loop. Yeah, there's nothing, you don't really need another inlet here, do you? It's always splitting up. Maybe for visual sake, it's kind of nice to have this extra node here. So technically, yeah, you wouldn't need it. Good catch. I think I'm gonna leave it because it'll help me spread things out. Or not, I'm gonna do, I'll drag it off. There we go. You're right, good catch, thanks. Yeah, so I was thinking like, oh, here's a node. What if something tries to feed back into it? I can add it in, but there's nothing that comes back. So you're right, no sum needed. Okay. Other path here. Okay, so we were going input and we're going to our delay. Got our delay, and notice that it wasn't -1, so I'm using delay instead of history. So I want to set this D value as a parameter, like we said here, delay. As I'm looking at this, I don't think a delay of 0 makes much sense, because if you're mixing this in at all, you're going to want some delay as a default value. So let me just say 10. Don't know why. Try that. You can leave it as 0 if you want, but I'm going to go with 10 here. Okay, so we go into the delay from the inlet. And then after the delay, what happens? These are all inlets. These are all parameters, things being modulated. And now it's going out here. And the shortest path to the output is through the mixer. So let's do that one first. And so we'll send it here. This is the wet input. Put that there. Okay. Well, what's going on here with this LFO and this feedback? Well, the first thing that we're going to have to do is probably set up this feedback, because, no, we can choose either one. So you can either choose this LFO, which will be modulating this value here, this rate value, or we could work on the feedback loop. I think this might actually be easier here, wouldn't it, right? Because you're just changing this one value here. So why don't we deal with that first? Okay, so it's not really showing it so much on the diagram, but what it's really trying to say here is this D value is going to change with this modulator. So let's grab what is going to be a modulator here. This is a cycle object. And so a cycle is basically a sine wave. And if we open up the help, it'll tell us it's an interpolating oscillator that reads repeatedly through one cycle of a sine wave. So it's a sine wave. it's a sine oscillator. So this can work. You can also use different modulators if you wanted to. If we open up the reference, maybe you want to do a different kind of modulation interface. You want to experiment with maybe a sawtooth, and you can use some of these other objects that are recommended by the C. Also, you can use a phaser maybe if you want a sawtooth modulator. But for now, I'm just going to use a cycle because a cycle is I don't know, it feels like a trusty modulator, right? It's my favorite. If you were to ask me, Isabel, what was your favorite modulator? I would go with a sine. I don't know about most people. Okay, so we're modulating this delay. Why cycle but not cycle tilde? Because in gen, nothing is tilde. Well, everything is tilde, but nothing actually, you don't actually need to write tilde for anything. Yeah, that's essentially why. Okay, so notice how we've already put this parameter delay in, but does that make any sense, right? Because we're modulating the delay. We can't just put in this value. So what we're going to need to do is basically, we'll have the cycle be the thing that is connecting to the delay. And then we'll set the original value of the cycle by some value. So if you think about it, it's like your modulator is, your sine wave is going at some amount, but then you want to change that. I don't know if that made sense. Let me try that again. So we're going to have this here. We're going to have to create some kind of summation section where we're connecting both our input and the modulator. Let me start patching and show you. So the input, you're going to need a sum. You're going to be summing in what you give as your delay. And you're also going to sum it with this cycle. So let me drag this out of the way. Basically what I'm trying to say is you're mixing the parameter and whatever you're giving as the modulator. Hope that makes more sense. So yeah, so we take this cycle and we sum it with our input here. And we give it, we're gonna have to do something before this, right? Because if you think about it, a cycle by default goes from -1 to 1. It's a bipolar signal, but we want it to be a unipolar signal, right? So if we do +1, so now this will be modulating from 0 to 2, right? That makes sense, yeah. Okay, and so now we're gonna want to multiply it by 0.5, so it's going from 0 to 1. But I'm thinking about that, right? And you're going from 0 to 1, but what if you want to play with that amount of modulation? You want to play with the depth of modulation. You can use that as an extra parameter. So that was the other one I was thinking of here. That I knew there would be one more parameter that wasn't on the diagram. So we've got here depth, and we'll say the default depth is 0.5. We're only doing a half strength modulator. And we'll say the min is 0 and the max is 1. That kind of makes sense, right? Here we go. So now we've got the selector here. Okay. And the other thing that we need to do is here, we have a modulator. This modulation here, and that's telling us the frequency of the modulation. And again, now we're mixing them together. So backing up, that might have been a lot all at once. What's happened here is we have this cycle. We're giving it some frequency modulation, this amount of modulation, this frequency, and that's the mod parameter. This tells us the frequency, and by doing this +1 and attenuating by a depth value, you're making it into you're taking you're going from bipolar to unipolar, and then you're factoring it by some depth that you want. And then once you have that signal, this modulation is modulating the amount of delay that you have already set, this base value, essentially. And that'll go into the delay here. And I think I probably have a question here about what I just said. So the cycle is actually cycle tilde, but not the real cycle, where it sends values simultaneously to different. Yeah, I think that's correct. Actually cycle tilde. Yes, exactly. This is like cycle tilde, not like the event-based cycle. Okay, so backing up here, what just happened? We've got our delay. We have an input parameter that this is like a static value. Then we also have this amount of modulation that's going on. And what we did was we turned it from bipolar to unipolar and attenuated. That's the key takeaway here. So now we're gonna go from, so we've got this modulated. So now we're gonna go out of the delay and work on the feedback. That's the last section we've got here. And so hopefully this should be pretty familiar because we've worked with a lot of feedback loops before. Now we've worked with our home filters and our bipods and so on and so forth. This was the kind of new tricky part that makes this what I would call level 3, is figuring out how to scale things properly and figuring out how, like, where your modulators go and where do you figure out your params. It's a little tricky at first and I stumble a little there. And so you can see this, maybe you spend some time with it, can sometimes forget what's going on. So don't worry too much if it gets a little confusing at first. Just do a bit more examples and it'll make more sense as you go along. But once you know how to do this, it shows up a ton as you're working with modulated signals. Anyway, so now we're working on the feedback loop. After delay, we go into this attenuation and it feeds back to itself. That should be pretty straightforward, right? Like we've done that before. We take our feedback, send it into multiply. Where did this come from? It came from out of delay, and it just sends it right back into itself, right? Why the +1 after the cycle? Okay, so that's because cycle goes from -1 to 1. And I wanted to scale it to be from 0 to some value, like 0 to 1. So if you go from -1 to 1 and you shift it up, then you go from 0 to 2. And then it's being modulated by a depth to make it back to basically a positive value. It makes it only positive values instead of negative modulations. Okay, so let's see. This should do something now. Let's try listening to it. I'm going to turn the try listening to this. Move on here. I'm going to turn it on a loop. Okay, so this is a completely dry signal. Let me set these values. And then turn up the mix. You know what? Let me turn the looping off. It might get a bit annoying. Something's going funny. What did we do wrong? Let's see. Oh, I have full feedback. That's probably why. I'm probably blowing everything up. Let me try again. Yeah, you can kind of hear that, right? It's just kind of like a flanger. Cool, so we've got that working. Questions here. One small clarification. When I see an LFO node like that in the block diagram, how would I know if it has to modulate samples between 0 to 300 or between delay value plus or minus modulation? In this particular diagram, a lot of times in the block diagrams, it doesn't actually tell you everything you need to know. And in this case, I actually don't know what would happen if I tried to do it from 0 to 300 or between delay value plus or minus modulation. The kind of thing that I would take away really here is like, you can try experimenting with other ones if it doesn't tell you in the diagram. Usually their supporting text will say like, oh, we'll modulate the delay tap by these values or something. It will tell you in the text, basically is what I'm saying. But if it doesn't tell you, it should. But you can try playing around and seeing what actually sounds good. In this case, you can go and try taking out the plus and see what happens if we do that. I don't know what's going to happen here, but we can try. Now I also don't have the depth set here. Don't have the depth, but you can play around with things and say like, okay, what's actually going to happen when I change these values? Yeah, so that's what I would say trying to do. But why don't we move along to get to the reverb so that we can get to the exporting step. And don't worry, the exporting step, the final section of things will actually be pretty fast. So we're doing pretty okay on time here. Let's not fill this. And yeah, so if you want to check out the example, I have things laid out a little cleaner in the solution with things cleaned up if you want to check that out. Yeah, and would the depth range being 0 to 0.5 make more sense? Yeah, actually that probably would, you're right. Good catch there. Okay, so let's look at what we're doing next. And so we're on to level 4, which is a reverb. And the reason this one is going to be a level 4 is because you can tell already that this is a little bit more complicated. There's a lot of different objects or different nodes here, and it's not really clear what they are immediately. It's like, what is an LBCF and what are these APs? And the key thing that we're going to learn here is what an abstraction, how to work with abstractions in Gen. Because if you click on this link where I got this from, again, this is Julia Smith, but there's a bunch of different different explanations of this. This is the free verb. So there's quite a bit of writing on this if you wanted to read more about it. But long story short is reverbs are basically sets of comb filters. You have a bunch of comb filters that have slightly different parameters so that you pick out different, basically you're trying to diffuse the amount of different frequencies. It messes up like the frequency response. And these happen all in parallel, and then they get summed together. And then a lot of times they go through all pass filters, and all pass filters basically mess up the phase so that it sounds like things are diffusing over time, but they don't change the frequency response. So there's like this part where you mess with the frequency a little bit, and then you mess with the phases so that things sound like they're in different times, and it kind of makes things sound like reverb sound kind of meshed together. That's the very simplified version of it, but if you want to learn more about reverbs, and it's kind of like kind of its own art form. And Sean Costello from Valhalla DSP writes about how he built Supermassive. This is a pretty recent thing, maybe about a year ago, or no, not even a year ago. This is like, I don't even know what time it is anymore. 2021, September 20th. Yeah, this was very recent. He talked about how he built Supermassive using Max, or some of the algorithms he tested using just plain Max. And so that's really cool. And the reason I bring that up is he talks about how it's a kind of useful environment for building reverbs, because you can build these, you could just set up all these different settings of all pass reverbs, or all pass filters and home filters and testing modulators and things like that. And it's like, that's how he made part of Supermassive. So that's a cool thing. I like to bring that up because kind of shows you that it is like a valid way of prototyping stuff. If it works for Supermassive, I think that's pretty cool. But anyway, so the way you can get started with this is thinking about comb filters, which we've already talked about and made abstractions for, and then all pass filters, which we'll talk about a little bit as we go through the steps here. And so this will get broken down into 4 different parts here. And that's why if you look in these templates, there are the 4 different parts. And what we're going to do is we'll go through how to make these LBCFs, which are basically a special kind of comb filter. It's basically a low pass. It does some low passing on the comb filter. And then we'll talk about how to make all passes and how to stick them all together. And that's how I'll get through this to get to the final result. So if you open up, yeah, I don't want to see the solution. Okay, so we'll start with part 1. And in part 1, we'll go through these low pass comb filters. Let's open up here. We're going to be focusing here on this LBCF. And if you look on the Julia Smith, the supporting text, he talks about what these are. And he's saying here where the what the F stands for, D and N stands for. You can go and read about this more, but essentially, that's what this slide is saying. This value is the feedback parameter. This is the damping parameter. And then this is the delay length parameter of your comb filter. So we've kind of built most of this already. Let me drag these things out. see it. As you can notice here, we've already done most of this, right? Like you've done the sum, and it goes into a comb filter, or it goes into a delay, and it gets fed back on itself. And then there's just this extra thing where it does a filtering. Like you're familiar with seeing this Z-1 from the biquad, right? It's just a smaller version of the biquad because it's just a one-pole filter. One pole feedback? Yeah, one-pole filter. Cool. So what'll happen in here, if we go back to our actual patching, is we're going to be trying to recreate this. And we're already pretty familiar with it, so hopefully this will be just another set of practicing. So we're going to only make one of these at first, because they'll all be pretty much the same, just with these different parameters change. Let me clean up for you a little. We're going to be making one of these, because then you can just take one and duplicate it and change all the parameters for each of them. We'll be abstracting things. Cool. So you'll notice that here I've got, this is inside gen. If I double click on this one and go inside, I've got my free verb title. But within that, you can create subpatchers. You can create a gen within a gen. And you notice that this doesn't have a tilde, because it's just, if you're making a subpatcher, like a subpatcher within gen, it's just called gen. And when I double click on that one, it's taking me to another layer of gen section, where you've got 4 inlets here. And what I'm going to do is be using inlets for the parameters, because I want to be able to modulate them at single rate. And it also is kind of nice to have them as a subpatcher, to have them just be inlets as opposed to parameters. It gets a little fiddly to start doing parameters within subpatchers and stuff. This is just my preference here. Yeah, okay, so what we're gonna do is have we'll have this basic, sorry. We're gonna have this inlet parameter, basically, or it's this inlet signal. We'll have the damping factor, which is going to be these factors. We're going to have feedback, which is this this amount, or sorry, this gain of feedback, this attenuation of the feedback, as well as the delay here. So let's go ahead and this over here, this over here, and zoom in a bit. Okay, so here we go. Let's do what we're used to. Rapid fire. Okay, first, sum from the inlet. And we're going to go to a delay with some modulatable amount. And that's going to come from here. And then that's going to go to the output. Okay, cool. Other loop. So what makes the most sense? Well, we're going to go from this, following the path. We want this, this damping. That's what this is. This is this filter part of the feedback loop. So, okay, so D2, so we'll call this damping. I have a note here that we're going to use D1 and D2 are just going to be, one will be damping, will be 1 minus damping. And the reason for this is just so that we don't have like so many parameters to deal with. It's just kind of turning into a macro, if you will, a macro control. And so in this case, I'm going to just do damping and 1 minus damping. And the reason for this is that those values together will work nicely, and you won't get any blowing up if these always sum to 1, essentially. So that's that. Okay, damping, I'm going to attenuate here. Multiply inputs, and that's coming from out of the delay. So let's bring it down here. Okay, and what happens after that? It goes to a sum. Yeah. After the sum, what happens? Well, it goes to this. There's a break. I think the simplest thing to do is this feedback attenuation. Move these out of the way. Oh, by the way, if you haven't used these before, you can use comments inside of Gen. If you just hit C, and you can type a comment. And it'll just be there to remind you of things when you run back. You know, comments are nice when you're programming stuff, right? Same thing in Gen. Okay, so attenuating the feedback that's coming out of this sum. And that will go back to the top. So I'm going to sum here, and right away I'm going to route it. Okay, so what else do we need to do here? Well, we've got to have this section before the split to the feedback. We've got to have another delay. So actually, this is just the history because it's one single sample. And that's coming from out of, which sum is this? Well, this is the second one. This sum that comes after the D2, after the damping. So after this here, we go from the sum to the history. Now we're going to need to have this attenuated before it gets sent back into the sum again. Okay, and so as I mentioned, I'm going to just make it this 1 minus damping. So to do that, you can do a new operator, and to do an inverse, subtract, reverse the subtraction, first input from the second. So in this case, I'm saying I want 1 minus the input I'm putting here. If I just did -1, it would say input -1. But in this case, I want to flip it the other way. I want it to be 1 minus the input. And that's true for other operators like divide. If you want to do the input divided by the value you're typing in, you would use divide. It's the same thing as in math. It's really what I'm trying to say. Okay, so we want this value here to attenuate what's coming out of history. So put it down here, multiply, and after that, we'll send it to the sum. So we just went here, D1, it's going to the sum that was the connect to this one. Okay, perfect. So as you can see, things start getting a little more hairy, and more pieces of the puzzle, but we can clean it up just a little bit, drag it up here, and you can do the usual right click and route patch codes. That cleans it up a little bit. If I had more time, I would probably spend a little more time to clean it up, but I've already shared some cleanup in the next step, so won't waste our time with that here. Okay, so we'll close this out and get back to things. Where was our original abstraction here? So jumping back, is it wrong to connect to the second input of the plus blocks? Nope, you can do either one. They all basically sum to the same thing. Or rather, all the inputs to sum, which is like a funnel, so it doesn't matter. Okay, so to recap what just happened, so I'm spinning up a little bit here, sorry. Let me know if I'm going too fast. In this, we just made an abstraction here, which is one of these LBCFs, and it has inputs where you can put the input signal. We can also send it in these different values that we want to adjust. And the reason I did it as inlets instead of parameters is just because it's a little easier to handle subpatch of parameters, in my opinion, when there's only a few of them, if you make them inlets, especially if you do this at comment, and you can tell yourself, you can remind yourself when you hover over it what this is. So when I hover, I see that's damping, it's feedback, and it's delay. Okay, so as I mentioned, all of these different parts contain the finished part of the original one. So if I'm speeding up too fast for you, either I can, I wouldn't worry too much. You can see the solution in the next part. You won't get left behind. Okay, so let me close out part 1. Get back to a little bit more clean slate. So this. Okay, part 2. Now we want to take, we've made one of these low pass comb filters, or the low pass feedback comb filters. And now we want to set them up in a parallel section. So how do you do that without having to repatch that 8 times or 7 times? Why would you do that if you can just copy and paste, right? But one thing I'll mention is like when you're working in Max, there are 2 ways you can duplicate things. One is to literally grab a copy of an object and duplicate, or grab a gen patcher. So create a gen patcher and say you have a bunch of these and you want to do it a bunch of times. You can literally copy and duplicate it, but each of these is an independent instance. What if you want to have something? What if you've already made some abstraction and you want to always be pointing to the same original source of truth, basically? The way to do that is to save something as as what we would call a gen DSP file. And I've already created that for you in this set of files we've got here. And the place I've put it is usually we call it in the code section, which maybe is a little confusing because they're patches basically, but they're gen DSP files. And I've already saved these low pass cone filters that we did in part 1. I've already saved that as a gen DSP file. And if you have this in the Max 8 packages directory, Max will already automatically know to look for this file within this directory. So when I say gen at file lbcf, that thing that we've just made in the past section has already been saved as an abstraction file. So anytime I want to use this abstraction I've made, like anytime I want to use one of these kinds of filters, I can just create one of these and it'll automatically make one of my files. It's very similar to how you would make an abstraction in Max if you're familiar with doing them that way. And you save them the same way. You open up a gen subpatcher, you do a save as, and you can save it as a gen DSP file. So we're starting section 2 and we're connecting our parallel comb filters. And so we already have the part 1 saved as a gen DSP file for you. And so all you have to do is duplicate 8 of these. And then we just hook them up. And this should be fairly straightforward because they're all the same. Grab this out of the way. See this either? Actually, we should. So the thing to notice here is that all the inputs will be going into, all of the inputs will be coming from in directly. So once you get 8 of these set up, just connect 8 of them. There's 8. It starts to feel a little tedious, but that's about as far as we have to go here. So these are all in parallel. And now you're going to want to set up the different parameters that we have here. So remember, we need our inlet for damping, feedback, as well as that delay amount. And so here we got our feedback, delay, feedback, damping, and delay. And so remember, this is one level in to our patch. Let's see, this is over here, right? Yeah. So we're only one level in here. When I double click this, we're here. So at this point, I'm going to make these parameters that we want. I want to be able to set this this feedback and damping. So what I can do is just do our usual param feedback, and I'll say it's 0.2, since most of these look like, or sorry, 0.84, because most of these look like that, and we'll give it a min of 0 and max 1. And we'll do the same thing there. It looks like the parameter for the damping is 0.2. So the default to 2, and we'll also give it a min and max. And the reason I know the min and max are 0 and 1 is because it says so in the text here. If you read through a little bit more about it, he mentions well, I'll promise you that it does say it in here. Yeah, low pass scale factor, feedback in the source initially set to this. Max size simply 1. Yeah, so if you look farther through here, it'll explain that that's why I picked those parameters. Okay, so now we need to connect our feedback, our damping, and then we'll need to connect these different delay amounts. Those are our 3 things we need to set up. Each of these uses the same feedback. So what I'm going to do is use something called send, which will send the value of feedback sorry, we'll need a send and a receive. So we'll have this receive, I'll call it FB, send FB. So this will take anything that comes into this inlet here, we'll send to the matching FB receive. So after this parameter is set, it'll say send, and then this receive will grab that amount and send it to the feedback. And now I see when I hover over that the feedback should really go in here. Cool. So this is an easy way to do things without patch cords. If you want, you can do sends and receives. As long as things are named the same, they'll connect from one place to the other with like virtual kind of cables. And so let me set up all the feedbacks here. Do that. And then we'll do the same thing for damping. Send. Yeah. Receive. Yeah, it's going to get a little messy. And once you hook this up, and then in the final solution one is a bit cleaner, so if you want to wait for that one, that's okay too. And then finally, what you would do next is set these values here. You set the different, for each of these parallel comb filters, you'll be setting the delay amount. And the way to do that is to create an F operator. And what's weird is you'll have to get rid of the default here. So I usually just scroll down to the F option and do space. And then you just type in the value you want. So even you can actually do an int value, constant integer, but for whatever reason, I just tend to do float because I don't know, it's just what I would do in this case. And so for each of these, you would set up the different float values. So you say float 1557, and you connect that to your first parallel, and you duplicate, and you say, okay, well, the next one is 1617. And you go on and do that for each of these parallel comb filters. But because I'm looking at the time, I'm getting a little, don't want to keep you just doing this tedious part. Let's jump ahead and say that you would do the same thing for the next steps. And if you open up the next solution, you could do this on your own. You see how this would work. But we'll do the thing with the cooking show where they just pull out the finished thing out of the oven from underneath here. Okay. I won't save this for now, but okay. So for step 3, what do we do for step 3? Well, now we need to do this AP section. And like I said, these are the series all pass filters. And in this case, you have a feedback value and a delay length value. And again, this gets described in the actual text of here, and it says the free verb all pass approximation. There's a little, talks about it here and sends you back to a block diagram. And the place I got the block diagram was following those links. So I see that this is an all pass filter that I would want to implement in Gen. And let's open up a template where we'll start. And so now we're doing the all pass filter section. And here's a cleaned up version of what we were just working on. They're all neatly set up with our damping values, our feedback values, and our delay numbers. So that's all set. And so now you would make an all pass filter here in this section. Let me pull this up. Okay. So now we're working on this little block. And again, this is fairly similar to the comb filter where I say, okay, well, instead of, because these are going to be subpatchers, I prefer to have them as inlets as opposed to parameters. And so in this case, I have a signal set up as my inlet signal, my outlet signal, and then also my two parameters are going to be this delay length here and this feedback amount. And so I would go ahead and do what I'm used to doing here. So I'll do plus because we've already got our inlet values or parameters basically plus. And then we got a history. Cool. So our inlet goes here, gets modulated by K1, which is our feedback value. The reason I'm calling this feedback is because this value is the same for both. So there's like a negative one and a positive one. So that's why I call it feedback, even though in this case it's not really doing any feedback. Anyway, so this is K1. Just to remind myself what this is. And so we got K1 is multiplying by this value after this first sum. And then it's going to this here and going out. We've also got this history loop. So instead of going into K1, we're going to go before that. Go after the sum into history. And it will be multiplied by, oh, you know what I did? This delay length needs to be modulated. So instead of -1 in history, we want it to be a delay. So in this case, we take this delay off. This comes from just a basic thing about all pass where you wouldn't be really modulating the delay length. Or in this particular example I took it from, they weren't modulating delay length. Okay, so after the delay, it goes through a negative K1 in attenuator. So we'll take this K1, multiply it by -1, so it's negative K1, and then we take negative K1 and then we do the attenuation of the delay. And then it gets fed back into this very first sum. And then we also see that there's, instead of being attenuated by K1, it also goes directly into this here. So see how it's kind of getting a little hairy here, but goes after the K1. But you can clean this up pretty well with some nice routing. Be careful moving around, but I'm gonna leave that to my past self, which has done the preparation before and made this a sub-batch for you. But basically, this is what an all-pass filter would be. And if you wanted to save it as a Gen DSP file, you would do a save as on this, and you could save it in your code section. Cool. So we're on to the final step. As I'm moving along here. You will create these in series. So what happens in this case is we're going to have to create we'll create a bunch of these all passes and put them in series. And they'll each be modulated with their amount of feedback and also their delay. And I'm going to be jumping through this quite a bit because I'd like to get to our export section, and I can answer more about this in the Q&A section after. But essentially what is happening here when you play around and go look through this is that I've duplicated two of these, the free verb sections, because there's a stereo, a way to make it stereo by basically increasing the delay of one channel versus the other. But I'd rather not speed through this too much, and we can go through it a little bit after because I'd like to get to the export section. And we can just work through the final thing and talk about the juice section of this. So sorry, I went a little slowly with the first sections, but hopefully having those foundations from the earlier parts will help you understand the this part if you go through it on your own. And you should be able to see what's going on here now that you understand a bit more about the gem patching. So I'll skip through this. And again, the slides will be posted on GitHub along with the code. And so basically, as I mentioned earlier on, is that this final code, this final solution of the free verb, we'll be taking this and exporting it to C++ and embedding it into a VST plugin. So what happens when you're working with Gen, like I mentioned, is it's getting compiled into basically like the compiled binary that is running within the host here. But you can also take that, that code and export it to C++, use it however you want. So I'm going to show you how you can actually export it. It's very simple. You just press, you just set up in a few message boxes here, and I can show you what files you need to include in a project, like what headers and so on, and then just a few tips, and you can go along with me as I'm doing this. So the place to start here will be, we can jump ahead to the finished solution, the Freeburg Part 4 solution patch. You can open this up. You can test it if you'd like on your own and listen to it and see how, when affecting the stereo spread, the damping, and so on and so forth, how it sounds like, well, a cheap reverb. And what you'll need to do to actually export the C++ is to go into your Max patch here and create a message box with the M key. And this is a special kind of object that you can send messages to Max objects. And you'll just write export code and create this message box, connect it to your Gen inlet. And then before you do this, you'll want to give a name to what you're exporting. So to do that, you can do it a few ways, but the way I like to do it is click on the Gen that you're trying to export and open this inspector tab on the side and find the section that's called export file name. In this case, I'm just going to give it the name gen_export. So that'll tell the exporter like what's going to be the name of like my C++ file basically. And so once you've got that set, you can do export code, and it should prompt you to like ask you where do you want to save it. And in the case of this patcher, you'll go into source and save it to export here. And you say open, and it should export your code now. And you can see in the console, if you hit this Max console, it'll say exported, it'll say where it went, and then it's exported the C++ file. So now we will be closing Max and moving on to, sure, I'll save it, keep that there. And now we'll be moving on to wherever you work with your compiler or your command line tools, because we're going to actually be building. So as I mentioned before, it gets named what you told them to name it. So if you go into your export folder, you should see there's something called genexport.h and genexport.cpp, and there's this extra library here called genDSP, and it has a bunch of headers in it, and then also the gen library CPP. So let me grab my slides here and make sure we're on this. So the thing that you'll want to know is that you need to include this genexport.h. You'll need to include all of these headers and sources, all these sources in your compilation step. And everything that you'll end up working with in the API is within genexport.h, which itself is fairly short. And if I open it up with Visual Studio Code, you can see that this tells you everything you need to know about your exported file. You can do things within this namespace of gen export, will be the name of your file, whatever you name your export will always be in this namespace. And then you can get the number of inputs and outputs. You get the number of parameters. You create the actual object using this create function, and it gives you a pointer to your object. You can destroy it when you're done. You can get this state, you can get the min and max of parameters, you can get the names, you can set, and almost, I would say the most important function here is the perform function, where you give it a buffer of type sample and a buffer of outputs, and you tell it how many number of inputs and outputs, as well as the frame size, the buffer size. And this will actually be where you run your gen code. Missed head export while trying to find the export file name. Oh, sure. you create a message box with export code and connect it to Gen and click on that and it'll ask you where you want to export it. Can you reopen? You'll create this and click on it, and then you should export it to this package's the workshop package source, and then the export directory. You should export it there. Cool. So the other thing that we'll get to here. So I was quickly showing that you can include the headers with this main header file, include all the sources. Perfect. And then let me show you for one other thing here. Open up the directory here. Basically, in this template that I've shown you here is basically the default plugin processor stuff that goes on with when you create a new Juice project from a producer or just from an example. And there's a minimal amount of things that are hooked in. The parameters get hooked into the Gen export itself and getting the min and max. Getting the parameters min and max, just calling in, this just acts as a wrapper around the Gen object that you instantiate when you create your plugin processor. Most of this is, you don't really need to know too much about Juice to know this, because you always do the same things here just to hook into your processor. This also exists as a repository on the Cycling74 website called gen-plugin-export. So if you ever want to check it out there as well. But both of these are basically the same source of creating a Gen object inside of your Juice plugin processor and then hooking up everything. And the key part being taking this export perform method and doing the perform of Gen within the processing block. And that's essentially all you need to do with Juice. And you can also, there's no editor that gets exported with Gen, because you're not creating any UI in Gen. But you can, of course, I left here a template for like the Hello World type editor. And if you wanted to plug in your own audio processor editor, you could do that. But for now, just use the generic one that Juice provides as default. Cool. So that's kind of like an overview of how you would include it. All you have to do is include gen export.h. And then anytime you want to use any of these functions, you prefix it with the namespace of the function that you saw in this export here. Anytime you want to set a parameter, you just access it from this namespace, essentially. So we can go ahead and get building and then have some time for questions, which I wanted to make sure we had time for. And so you can be doing this from any IDE you want, really. But most of this will just happen on the command line, honestly, because you should have CMake installed, as I mentioned, CMake version. I'm currently on 3.20. Shouldn't matter too much which one you're on. Recent is good though. So in your terminal from within this workshop directory, so again, this is likely in your package, Max packages, this workshop, you'll want to create a build directory. So just make dir build. And then you'll also want to make sure you have the Juice submodule that has been included within the library or within the source here. This is a submodule, so you want to do git submodule update --init recursive, run that. In the way. I already have it checked out. This might take a few seconds for you. This is as a kind of a got you at the moment because I'm running a very recent version of Max. This is pinned at, I think, Juice 6.01. There's some define in Gen that if you're trying to run the most recent version of Juice and the most recent version of Gen, there's like a macro that kind of gets messed up. So if you happen to have added this as your own submodule in some project you're working on, that might cause an issue for you, but Currently it's working on 6.0.1, and we should get a fix out for the gen issue there. But just as a kind of a heads up, gotcha, that's something to keep in mind. But yeah, so you should have a get some module update. And now you should have juice all checked out here within the source directory. And that's like an easy way because of the way the CMake lists has already been set up in this template here, is expecting juice to be there. But if you wanted to use your own version of juice, you can just simply point it to the right place here in CMake. In this case, I'm adding in CMake as a subdirectory in this root here of the source. If you're not really familiar with CMake, I wouldn't worry too much about this stuff. You can go ahead and look it on your own time, but this is a place, what I would say is a simple place to start if you want to work with CMake and Gen. This idea of looking for these exported libraries, this is what you would include, and so on and so forth. CMake is just nice because it's platform independent. So if you're working on Windows and Mac, anybody working on this together, like we can be doing this at the same time. Anyway, hope that makes sense. So we've made our build directory. We have our submodules checked out. We'll go into our build directory and we'll run CMake to generate the project. So this is like, instead of using the producer to generate a juice project, this is doing it with CMake basically. So I'm going to give it basically the X code. You give it -g/ your generator, or you don't want to specify it, it'll just pick a default. So I'm just gonna do CMake ... And what is happening here is you're in the build directory and you're saying, okay, my base CMake list here is in source. So I say ... source. And it's saying configure based on the CMake list, which is telling it where all of these different export includes and so on and so forth are living. So it tells it where to get the base configuration from. So we run this and it'll find your compiler, should find, likely I would guess it would find Xcode if you're on Mac or Visual Studio if you're on MSVC if you're on Windows. And it'll be configuring juice here for you and setting up all these different includes and basically gluing together everything to create a build project or an IDE project for you to open up. Well, let's let this go here. It takes a little bit the first time because it basically builds this, as far as I understand, it builds like a special helper that this juice aid. I think it's a binary that is helping figure out which includes from juice you need to have. I'm not an expert on that, so I'll leave it at that. So once you're done, it should say that your build file is written to your build directory, which is where we are. And then the final thing to do is to run CMake from this build, CMake -- build, and you point it to that same folder, and it'll run this. And this is compiling your final code here. So it knows which things to compile and go ahead. You repeat this first CMake command. You just do from the so say you're in the root directory of of this repository. You go to cd build, and then so I'm trying to copy it into the command line here, or sorry, the chat window here. Cd build, and then you do a cd. CMake ... / source. And that should generate your CMake directory. And then just once again, I'll put it over on the side here if you're still following along inside of build. Once you actually have things configured, you run CMake -- build, and then you save it. And that's what's running here right now for me. So once everything is compiled, it'll tell you that you've created your final module, and it's created the artifacts, which will include a VST3. And so if we go here into build, I can look in the side, look in like Finder or Explorer or whatever, but you can also find it here in the artifacts. You'll see that it has a VST3 and it's created this VST bundle here, or reveal in Finder. And so this is the final thing. So in this case, it's Gen Freeverb. I named it that. The place you actually name your VST is up here in the CMake list. Set Gen plugin name, Gen Freeverb. If you change this value here, plug in here. that would change based on whatever. And if you also want to change what like the product name or the bundle ID, these things, you can change them here in CMake as well. But that was a whirlwind tour of how you would just, you would go ahead and actually build your exported code. And to test if it works, one easy way to do it is to open a new Max window and create VST, a VST tilde. So a new Max window, create VST tilde here. And then you've got your build folder open up somewhere, so maybe Finder or whatever. And you drag this VST3 bundle onto your VST, and it'll load it in for you. Snapshot, oh yeah, okay, that's fine. And then if you want to actually see that the parameters are there, you can do is open the inspector. And inside of here, you can find there is a show controls in Patcher under the appearance. So all the way on the top, if you're in all, you say show controls in Patcher. It'll show it as a kind of like as you expect, like in a DAW, where you like open up the controls and it shows you all the visible parameters. And you can see here that all the parameters that we exposed are now available. And if you want to look in, if you're in Max and you want to look at a VST, you can open the native editor, and you can see here it's also opened it up. You can change these values, essentially the same thing. But then if you want to go ahead and test it, you can just set up your demo sound patch and then connect to a DAC, and it should be good. But I want to leave some time to see if people run into any errors, and we can try to debug those. Okay, so Murphy. So if anybody has any issues that they're running into, feel free to put it in the Q&A section, or if you have any errors, or if you want to come up and share your screen, we can try to debug those. I can allow you to come on our virtual stage, try to work those out if you'd like. So let me know. Yeah, and if you get a bunch of no expanded from macro JS, yeah, so this might be because of that juice issue. So let me try one thing for you. This might work for folks. So if you CD into your source, ls, okay, CD into juice. If you do a git status, you might be on the main branch, so you might want to be checking out I would suggest checking out this 6.0.1 tag. I believe to check out a tag, you just do git checkout 6.0.1. And that should get you checked out to Juice version 6.0.1. So if you do that, I would recommend trying rerunning the CMake generate step. So the CMake ... from the build directory, regenerate to make sure the right juice is included, and then run the build step again and see if that doesn't fix it for you. Oops. Yeah, so this thing about running into the LBCF object being empty, it might be because it's not on your max path. If you have, that might be one guess, is that if it's not your package directory, it won't automatically be found. I could be wrong on that though. Sometimes max path stuff, especially if you're on a newer OS, maybe something's going kind of a little fancy there. But that's also another way, is to drag it directly from the core folder. Unknown CMake command, juice add plugin. Do you have the sum module checked out? If you open up juice, is there stuff in there? Okay, so you'll need to do this git sum module update command. And that will check out juice here into the right direction. So going through this, I should put in the README what you do. Oops. Oh, I pulled the BST into max again. Yes, sure. So created a new max patch, created BST, create the BST tilde. And then in a Finder window, or I believe Explorer window, you can find the bundle. And you can just drag it onto the VST object and it'll load the right one. This also should work if you go to your plugins directory and it's been scanned. But because this is getting built to a build folder, and it's not like on whatever path is expected, it's easiest just to drag it onto the object in my experience. If you want to test right away and make sure it's what you want, and then you can bring it to wherever you normally keep your VST bundles. And then if you want to do the view the controls, you open up the inspector, go to all and show controls. You check that off and it'll change into whatever. Nice. Got some people. So rather than me putting in this here, I will point out that there is also an existing GitHub repository that has Gen plugin export. I'll share that with everybody as well in these slides at the end so you can take it home. There's an existing Gen plugin export directory that, project where it has documentation on how to all do all of this. And it kind of sums up all these steps. So if you run into trouble, it's a little better. This is getting updated as well for the recent versions of CMake and things like that. So that should be clear. Is anybody still getting any compilation errors that we can try to help out with here? Again, thank you for patience with spending so much time with learning Gen and then kind of getting through this a little quickly. I think this is something that you can, it's a little easier if you're not doing it in interactive ways, figuring out these compilation errors, and I'd be happy to stick around to try to help this out. But thanks for making it through the quicker end of this. Glad to see it's working for a lot of folks already. It's really cool. Yeah, the perform is just like the process method you use in any other effect. If you look a little closer at it, you can see exactly. It's just getting wrapped. Looking here. Sorry, where's it going? The process block, you literally just take these input buffers, process it, and then send it back to the buffers you usually do in Gen. How do you expand the VST UI and Max? You saw the sliders. you go over here, you click on your VST object, and then in the inspector window, to go to all and show controls and patcher, you check this. And then if you want to open up the actual native view, you do open native editor. And it will show whatever UI you've created, in this case, the generic one. Well, if there aren't any more questions, oh, there we go. Oh, somebody wanted to know how do we get the key press to show up? There's a, I use this thing called Keycaster on Mac. I believe it's open source. It's pretty nice. Would recommend. Another question, is there a way to have the original parameter value ranges preserved in the default juice editor, not referred to norms? And that might actually, that's a good question. It might be something going on with the generic plugin editor, possibly. I have to take a look at that. Get back to you. Yeah, this is a great thing to mention. Somebody says here you can release, there's mod Dorf pedals that make it easy to run these patches outside the computer. And as I mentioned really early on, there's like our gen patches you can export because of this feature. There's also Daisy patch Eurorack modules. There's a bunch of these that you can find related to gen. You can find these, we have a bunch of these public repositories. They're different packages in Macs that allow you to take gen patchers out onto like hardware devices, which is pretty cool. So once you know how to do a lot of these, once you know the patching techniques, you can take a lot of things outside of Macs just doing that, yeah. The place to look for that is in the package manager, usually in Macs. So if you, in your inside Macs, you click on this here in the package manager, there's a ton of different options here. So like, I think there's the module. I'll leave that to the reader to go check this out. But yeah, that's something you can check out, because beyond Juice, if you know the C++ API, you can make this work in lots of different environments, which I think is a lot of fun. And so somebody asked about other resources for audio DSP introduction that I recommend. Yeah, I would say those online books it's just amazing that those are all available, but you can also, there's a lot of things on the Digital Audio Effects, DAFX conference. There's a lot of free papers that you can look at. I think it goes back till 98. You can find tons of papers here with all sorts of different things you can learn about. And that's one place you can find like more cutting edge research. But yeah, I'd recommend that. Somebody asked, once it's built, is there another command to do in order to create the VST file? So it sounds like maybe you've generated the CMake project, but not actually built anything. You would want to run CMake -- build and then dot while you're inside the build directory, and that'll run the actual compilation. But yeah, no, there's tons of things for DSP that's available online. This is one I would look for if you want to look for like actual block diagrams, or for just like general, like what's happening in DSP. This is one free place. If you're in the Audio Engineering Society, there's tons of things there. Anybody else, if you want to chime in with your favorite things, those are some of the places I go a lot. Yeah, that's what I would suggest. Yeah, somebody asked about the last part being way too fast. Sorry about that. This should be available. I don't know how quickly, but it'll be fairly quickly after the presentation's over. It'll be released for attendees, and then later on it will be released for other folks. Resources for reading these block diagrams. It's kind of tough to say. I wish I knew of better solutions, but the ones that I've learned are trying to like reverse engineer stuff, either looking through open source plugins and seeing like, oh, it came from this paper, and then looking at the paper and seeing the block diagram and how did they turn that into code. But for Gen particularly, I would say try to find a lot of the examples come from very like easily available like reference papers that are in the patches. And I would say open those up, find the patches and try to like match back and forth what's going on. And you can practice that way. But after a while, a lot of them you start to see that they use very similar pieces, and it's more about how you connect the pieces than anything other than that. Yeah, the -- build and -- config options for CMake are enough for these gen-based plugins. Source file. Does the file exist there? Well, as we finish rolling over into things, feel free to leave if you don't have any questions, but I'll stick around to answer any other folks' issues for next. I think I have like another bit of time. We can also head into Gather Town. So the file doesn't exist, but did export to that location. So other files are in place. Did you name it something else possibly instead of gen export? It'll need to match up with the CMake value. So these folks running into missing file errors, are you running from the build? Did you create a build folder where you generated your CMake files? Did you create this build here? I can run through the steps again if folks want to see that. I think that might be helpful. Let me step through it one more time, just so that might help some people. From the solution patch. Okay, so if you start from the part 4 solution, go to the gen, click on gen, and then the inspector under all, make sure you've got the export name to be gen export. Once you do that, you can hit export code, and it'll ask you where to put it, and you'll want to put it into source export, and check in here that everything is named, or check that it's named gen export.h and gen export.cpp, and you've got all your libraries here, or the gen DSP library. Once you do that, open up a terminal window, create a build directory, make your build. Make sure you have your sun module. So you do a git sun module update init recursive. In this case, I've already have it, but this might take a little bit. Make sure that juice is pinned to the right version, but it should be if you're just doing a get some module update in it. So we go into build, and then from inside build, we do cmake dot source. So this is from inside. So this is where folks are running into Poole. So this is helping some folks. The naming step. Cool. Yeah. Thanks everybody for being patient. So then once this finishes configuring everything, that's when you run the build and you'll actually create the VST. So let's say build files have been written, and inside of build, you run cmake -- build, and it'll build for you. What is the title param in Gen? That just tells, it just says that when you open up the patcher, it gives it this, the title. Doesn't do anything for the actual export. So we're getting past time. I think the best thing to do here is to move discussions into Discord, perhaps. Discord or GatherTown. I think Discord might make the most sense here. Thanks everybody for sticking around. Like I mentioned, the video will be available. All the solutions, again, are inside of the repository. I'll be updating the repository with some extra steps of this last bit that went a little bit fast so that you can go back and see it in text if that's helpful. If you have any questions, yeah, so I'll stick around in Discord and I'll be around all day and answer questions. So thanks everybody.